Hello and welcome to day 2 of ATMOS 2750. We're focusing in today on an introduction to the atmosphere, and if you're an atmospheric science major, you've probably seen all this stuff before, and you probably don't even have to watch it, and that's fine. But not everybody in this class is an atmospheric science major, and I'm going to assume that you have no knowledge of the atmosphere as we move forward. So today we're just going to cover as to why does the Earth have an atmosphere. We'll introduce the composition of the Earth's atmosphere, the temperature scales that we use to describe the atmosphere, the vertical temperature structure of the atmosphere, and then we will define pressure. So when you look at this image, this is an image that was collected by Apollo 8 in December of 1968. It has a very famous name. It's called Earthrise, and it was one of the first pictures that we had to show the fragility of our planet and that we're all living on one blue marble, essentially, in the vastness of space. It, in part, kind of helped spawn the environmental movement in the late 1960s and inspired the creation of Earth Day, which is an annual event. So if we look at the visible image of the Earth, what would an observer in space notice about our planet? Well, it kind of depends upon your perspective. So as an atmospheric scientist, I look at this and I see clouds. An oceanographer would look at this and see oceans. A geologist would look at this and see land masses. A glaciologist would look at this and see ice. And we have all these different spheres. A biologist would look and see life. We have all these different spheres of influence associated with the Earth. The hydrosphere is the water in the system. The lithosphere is the land. The atmosphere are the gases surrounding the planet. The cryosphere is the ice, and the biosphere is all the life that's contained therein. So here we have the planets in our solar system, and I'm going to be a snob, and I'm always going to say that Pluto's a planet, even though it's been demoted to dwarf status. So we have the Sun, and we have the 9 planets. So which of these have atmospheres? Well, Venus has an atmosphere. And in fact, its atmosphere is much more dense than Earth's. Mars has an atmosphere, but it's much less dense than Earth's. And then we have the big gas giants, Jupiter, Saturn, Uranus, Neptune. They're the gas giants. They have very thick atmospheres, but not a rocky surface per se. And then we have Mercury and Pluto, which have almost no atmosphere at all. Sort of thing. So what's the difference? Why do they not have an atmosphere? Why do the gas giants have such huge atmospheres versus the rocky planets? Well, one of the important things is gravity. So if you happen to have a source of gases to the planet, then if you don't have enough gravity, then it's possible to lose those gases to space. So the higher the gravity, the more likely you are in order to retain the atmosphere. But you still need that source of gases. For our planet, the source of gases is volcanoes. For a lot of other planets, they also have volcanoes. But early on in the formation of the solar system, there was also a lot of just accretion, gathering up of gases through gravity. There was also comets that were a source of volatile species as well. But even if you have gravity, and even if you have a source of gases, you can still lose your atmosphere over time if you don't shield it from the solar wind. The solar wind is a series of essentially charged particles that are streaming out from the sun. They're very energetic, and when they strike a gas in the upper part of the atmosphere, they excite that gas, increasing its kinetic energy, increasing its velocity, and if they increase the velocity to beyond the escape velocity for the planet, then we lose that gas over time. And that's exactly what we theorize has happened to the Martian atmosphere. Mars used to have an atmosphere that was probably about as thick as the Earth's, but over time, the solar wind has eroded that atmosphere away, in part because the Earth has a magnetosphere, which helps protect us from the solar wind, and the magnetic field on Mars is much, much weaker than that on Earth. So now we can look at the atmospheric composition. Basically, we divide the composition of the atmosphere up into permanent gases and into variable gases. The permanent gases, it doesn't matter where you go in our planet in the lower part of the atmosphere, from Salt Lake City to the South Pole to the top of Mount Everest, the concentration of these gases is going to be the same because they're well mixed. Why are they well mixed? Because they have very long lifetimes in the atmosphere, which allows them to be mixed up over a period of time to where they're well mixed. Nitrogen, N2, which has a triple covalent bond, which is very stable, makes up about 78% of the atmosphere by volume. Oxygen, two oxygen molecules connected by a double covalent bond, which is also fairly strong, makes up almost 21% of the atmosphere. And all of the other permanent gases, mainly the noble gases, argon, neon, xenon, make up the rest of the almost 1% of the atmosphere. And we can contrast that with the variable gases. The variable gases are those that have variations in the concentration as a function of both location and time. So these are gases that do not have long atmospheric lifetimes and are therefore cannot be well mixed. They have sources, they have sinks, and near the sources the concentrations are high, and after the sinks have done their thing, the concentrations are low. The most abundant variable gas is water vapor, which can make up anywhere between 0 and 4% of the atmosphere. So if it makes up 4% of the atmosphere, it has to displace nitrogen, oxygen, and the noble gases in order to take up that much of the volume. But water vapor concentrations are highest over warm bodies of water and are coldest at high altitudes and at extremely cold temperatures. Then we have carbon dioxide, which is a trace gas, a greenhouse gas. This slide is a little bit dated. This says 360 parts per million, but it's continually increasing due to the combustion of fossil fuels. And it is now up over 400 and actually up around 410 parts per million. So what that means is that if I grab 1 million molecules randomly from the atmosphere, 410 of those will be made up of carbon dioxide. So why do we care about carbon dioxide if it's so rare in the atmosphere? Because even at those low concentrations, it is capable of absorbing outgoing infrared radiation in a wavelength band that would normally go directly to space. And even the addition of a small amount of carbon dioxide can absorb that infrared radiation that would otherwise go to space and retain it longer in the system, which would thereby cause heating of the system. Any greenhouse gas can do that. Carbon dioxide and water vapor are both greenhouse gases. Methane is the third most abundant greenhouse gas. It's also known as natural gas. It has many natural sources. Then we also have ozone a little bit further down, which is 3 oxygen molecules put together. Ozone can be both good and bad. Ozone in the stratosphere up high above the surface is actually good because it absorbs the much of the incoming ultraviolet radiation from the sun. Ultraviolet radiation is dangerous because it causes skin cancer. And then ozone down where we live, down in the troposphere, is actually dangerous because it's harmful to plants and animals. Through the process of respiration, it damages tissues. Then we have particles in the atmosphere. That's my area of expertise. And then we have the chlorofluorocarbons, which are actually available in parts per trillion in the Earth's atmosphere, but are still important from an atmospheric chemistry standpoint. And we'll learn more about that when we start talking about the Antarctic ozone hole. So if we want to define temperature, temperature is defined as the average kinetic energy of the molecules of a substance. Kinetic energy is the energy of motion. And so at high temperatures, we have a lot of motion, of vibration of the molecules of a substance. And if you slow things down and you reduce the molecular vibrations, you are actually lowering the temperature. Until, of course, you get to absolute zero when there is no molecular motion. So the temperature scales that we use are the Fahrenheit scale, the Celsius scale, and the Kelvin scale. So for the Fahrenheit scale, it was created by scientists who created their own liquid thermometer that had no scale in it. And what he basically did was he picked a very cold day in winter in Europe and marked that as 0 on his thermometer, and then took a very hot day during the summer and marked that as 100. And that's how the Fahrenheit scale came about, from one person's thermometer that they made in their laboratory, as opposed to Celsius, which defines the 0 point as the freezing point of pure water and 100 degrees C as the boiling point of pure water at sea level. And of course, the Kelvin scale just adjusts the Celsius scale to absolute 0, so that when the temperature in Kelvin is 0, all molecular motion has stopped. If we combine the temperature scales together into one chart, you'll see that the freezing point on Fahrenheit's liquid and glass thermometer just happened to be at the 30-second tick. So 32 degrees Fahrenheit is the freezing point of pure water. 0 degrees Celsius, and then 273.15 Kelvin. The boiling point of pure water on Fahrenheit's liquid and glass thermometer just happened to be at tick number 212. The Celsius scale is defined as 100, and the Kelvin scale is 100 greater, is also a difference of 100 between freezing and boiling point, so it's at 373.15. The difference between the temperature scales is between the freezing and the boiling points of water on the Fahrenheit scale is 180. For Celsius and Kelvin scales is 100. And this actually allows us to quickly be able to do a conversion, a mental conversion between degrees Celsius and degrees Fahrenheit. So for example, a 10-degree change in Celsius is equal to an 18-degree change in Fahrenheit. So if somebody tells me it's 10 degrees Celsius outside, I can immediately figure out, oh, well, it's going to be 32 degrees Fahrenheit plus 18 degrees Fahrenheit. So that's going to be 50 degrees Fahrenheit. Somebody tells me it's 20 degrees Celsius outside. Well, I start off at the 0 point, which is 32 degrees Fahrenheit, and then I add an 18 for 10 degrees C, and then add on another 18 for 20 degrees C, which is now going to get me up to 58 degrees, and so forth and so on. I have an active learning exercise, which we would normally do in class, but I'll make those available. But basically, it's testing your ability to do mental conversions between the temperature scales. And of course, one notable fact about the temperature scales is that the Celsius and Fahrenheit temperature scale coincide and are exactly the same at minus 40 degrees. So minus 40 degrees Celsius is equal to minus 40 degrees Fahrenheit. So how does temperature change with height? Well, here we have an image that is showing the altitude from 0 all the way up to 120 kilometers. So this is basically going from the surface all the way to space. And then we have the temperature in the two different scales, the Celsius scale and the Fahrenheit scale along the x-axis. So in the lower part of the atmosphere, the temperature is decreasing with height, and then it stabilizes and then starts to increase with height until you reach a maximum at about 50 kilometers, and then it starts to decrease with height again, reaching a minimum at about 90 kilometers, and then once again increasing. And what you want to think about is that in the lower part of the atmosphere, why is the lowest part warmer? Well, the atmosphere is basically going to be warmer when it is closest to a heat source. So what is the heat source for the lower part of the atmosphere? It's the solar radiation that is being absorbed at the Earth's surface and then transmitted to the atmosphere via radiation conduction and convection. The further you move away from that source of heat, the colder it's going to be. Much like moving further away from a campfire, you'll get colder and colder as well. And the temperature of the atmosphere would continue to decrease until you got up to the upper part of the atmosphere, if there weren't any heat sources in the atmosphere. But we do have a heat source in the atmosphere, obviously, because the temperature starts to increase at about 20 kilometers, reaching its maximum at about 50 kilometers. What is that heat source in the upper part of the atmosphere? It's the absorption of ultraviolet radiation by molecular oxygen and absorption of ultraviolet radiation by ozone. Both of those molecules have very strong absorption bands for ultraviolet radiation, which protect us from being exposed to that radiation at the surface because it's being absorbed much higher in the atmosphere. And then basically, once we have these different temperature regimes, we use that to define different layers of the atmosphere. So the lower part of the atmosphere, where the temperature is decreasing with height at an average of 6.5 degrees Celsius per kilometer, we refer to that as the troposphere. That's where all the people live. That's where all the land masses are at. And then where the temperature is increasing with height, we refer to that as the stratosphere, up to about 50 kilometers. Beyond that, we have the mesosphere, where the temperature is decreasing with height. And then beyond that, we have the thermosphere, which is where the solar wind is interacting with the molecules on the upper part of the atmosphere, making them more energetic. In this class, we're going to primarily be working in the troposphere, and then we have, when we're talking about the Antarctic ozone hole, we'll be talking quite a bit about the stratosphere. So if we look at what fraction of the mass is contained in each of these layers, 90% of the mass of the atmosphere is contained in the troposphere, 9% in the stratosphere. That's 99% of the Earth's atmosphere, with less than 1% of the atmosphere in the mesosphere and thermosphere combined. So here's a slightly different perspective for the layers of the atmosphere. The red line is essentially equivalent to what we were just showing before with the troposphere, the stratosphere, the mesosphere, and the thermosphere. But this goes, instead of going up to 120 kilometers, goes all the way up to 500 kilometers. So this goes up to low Earth orbit. And the reason I include this here is for the green line, which is the homosphere and the heterosphere, with that dashed line between the two at about 80 kilometers or so. Everywhere below 80 kilometers, the atmosphere is well mixed and the permanent gases make up their respective fractions. Above that, you start to have differentiation based upon the molecular weight of. So you have the hydrogen and the helium, the lightest gases, will start to dominate at these high elevations. So what is pressure? Well, pressure is defined as the force applied divided by the area over which that force is distributed, force divided by area. So here we have a telephone booth, and you can imagine some crazy college students that maybe want to see how many people they can get in a telephone booth. And so the person at the bottom, they get in and they say, okay, this isn't too bad. And then somebody climbs on top of their head. There's now more pressure on them because there's more weight above it. And this will continue. And as the mass above the person at the bottom continues to increase, so does the pressure on them. The person on the top has very little pressure on them because they don't have much weight above them at all. So we actually define pressure in the atmosphere as the weight of the gases that are above. And basic definitions that we had from the beginning, from the atmosphere, the hydrosphere, the cryosphere, the lithosphere, and the biosphere. And then we have mass, volume, density, and pressure.